All right, class, welcome today. We're going to go over the concept development that I left you with here. So let's go, first of all, situation 3. We're going to talk about the ball or system, and let's talk a little bit about the work that is done. So just a real quick reminder, let's switch over here to the notes, that in general, what happens here is if our force and displacement are along the same direction, that's a 0 degree angle, and that means positive work is done. Again, 0 degrees would give us a positive, it would return a positive number for the cosine. And that's actually true for anywhere along this region here from 0 to 90 degrees. Likewise, if our force and displacement are in opposite directions, we are at down here at the -1, so that would return a negative value for the work. And again, that's really true for anywhere in this region here. Okay, actually going up here as well. If they make a 90-degree angle, in other words, if they are perpendicular or they're at 270 degrees, you'll notice that that returns a value of 0 for the cosine function. So that would actually make 0 work being done in this case. So just those quick reminders as we think about the work that's being done here. All right, so for this situation, this is situation number 3, we notice that the applied force is up and the displacement is downwards. That would be 180 degrees, which would give us negative work. Since the applied force is by the hand and the hand is not part of our system, this would be an external force, which is doing non-conservative work. Okay, so NC for non-conservative. Gravity is a force right here. It's on the ball by the earth. The ball and earth are both part of our system. This would be an internal force. Internal forces are going to cause conservative work to happen. And again, they are actually in the same direction, so that would give us positive work. We also notice that this object is accelerating, which would tell us that this gravity must be larger than the applied force. In that case, there must be a net positive work being done. Okay, moving on to the calculations. Of course, these are the known pieces of information up here. Basically, I'm just applying our equations of energy. We have the mechanical energy of kinetic energy here. It's 1/2 mv squared. So I calculate out 1/2 joule. Potential energy is calculated with mgh. These are the values that we were given. So we get 20 joules of potential energy. I can put that on my graph down here. I've used about 4 joules per block. So we have 4, 8, 12, 16, 20 joules of potential energy. Here's my 1/2 joule of kinetic energy. The next thing that we were asked to do is find the non-conservative work. Okay, find the non-conservative work. And that is done by the thing that does non-conservative work, which is the applied force. So I need to know my applied force. Turns out that it's 8 newtons. And again, this, I'm not going to really explain this. We've done this plenty of times. We put that applied force into our work equation, where we have 8 newtons. It moved 2 meters, and then we're dealing with the cosine of 180, which will give us -1. And that would give us a total work that's non-conservative of -16 joules. So my non-conservative work is down here. This is essentially removing 16 joules of energy from this system. Okay, so the system has a total. If you combine this all together here, we've got the 20 joules of potential, 1/2 joule here. So we're talking 20.5 joules of energy there. This 16 joules of non-conservative work removes that from the system. So again, my accounting system here is simply looking at ins and outs of the energy. The energy is being lost from our system. It's being lost in the form of the applied force, and that removes that energy, leaving us with 4.5 joules of kinetic energy. All right, let's see what else we were trying to find. Oh, should mention here that we set the height at 0. Again, this is our lowest point. So that's a really quick, easy calculation where the potential energy is 0. All right, I'm going to skip down to situation number 5. Okay, situation 5. Again, let's go through our work energy table. We notice here that the normal force is perpendicular to the displacement, so that's 0 work. The floor is not part of our system, so that's non-conservative. But again, since it's doing no work, I mean, it's really not going to change the energy. Our friction is actually opposing the displacement. That's going to be negative work. And again, the floor is not part of our system, so that's non-conservative. It's an external force. Gravity is on the ball by the earth. That is part, okay, I'm sorry, it's a box. That is part of our system. That is the only conservative force that we have. It does no work, but it would be a conservative force. And then our applied force, again, hand is not part of the system. It will do non-conservative work. It is in the same direction as my displacement, so that is positive. All right, now, the net work being done, because we're ultimately losing energy from our system, okay, we know we're getting slower, potential energy is not changing, potential energy is actually 0. We're going to be losing kinetic energy. So that's going to give us a net negative non-conservative work. All right, let's get to the calculations. Once again, potential energy, because we're basically on the ground level, staying at the ground level, let's just make it 0. Make it easy on ourselves. Kinetic energy, we have 1/2 mv squared, mass is 10, velocity is 5. If I've done my math right here, we get 10 times a half gives us a 5. 5 squared is 25, so that gives us 125 joules of energy. All right, I'm going to put that on the graph. I used my scale of 25 joules per box, so my kinetic energy here of the system is due solely to the kinetic energy. There's 125 joules of that. The work done by the non-conservative forces, then, let's take those in consideration. We were told, if I'm not mistaken, yep, there we are. Our applied force was 12, so we're going to do 12 times 5 cosine of 0. That gives us 60 joules. Our work done by the friction, that's the, again, it's removing energy from our system, right? We already said this up here. And it's removing 110 joules. The total done, and we'll use this in a little bit here, the total is simply combining those together, figuring out how much work that does overall. All right, so down here, my applied force, the applied force did, where's my number here? It's 60 joules. There's my 60 joules of positive work. Here's my negative 110 joules of, that's the negative work, okay? Negative work on the system. So essentially combining these two together, okay? Combining these two together removes a total of 50 joules from the system. Notice my system here is now down 2 boxes because it's lost 50 joules of energy. So again, accounting for the ins and outs, in a system, we just simply, again, pretty much put them all together here to figure out what we're left with. Okay, let's take a look at some unit analyses. So going back to when we first learned about forces, we understand that a force is measured in newtons. Now, in fundamental units, of course, mass is measured in kilograms, acceleration is measured in meters per second squared. That gives us a newton being equivalent to a kilogram meter per second squared. That's going to be important here in just a moment. Let's look at our work equation. Work is equal to FD cosine theta, where the force is in newtons, the distance is in meters, and cosine theta has no unit. So basically, a joule can be thought of as a newton meter. Okay, we read this when they're next to one another here like this. A newton times a meter is just written or read as newton meter. So joules are newton meters. All right, potential energy, also measured in joules. also measured in joules. But let's think about what's going on here. We have mass in kilograms. Our gravity constant this is our not electric field, sorry, gravitational field, newtons per kilogram. Of course, we can see those kilograms are going to cancel out. And once again, we are left with a Newton meter being equal to joule. We'll come back to this in just a moment. Let's take a look at it from the kinetic energy perspective. Once again, kinetic energy measured in joules. Mass is kilograms, and we're taking velocity measured in meters per second. We're squaring it. That's going to give us a meter squared over a second squared. So a joule can also be thought of as a kilogram meter squared per second squared. So that's where I want to come back up here now. And basically, if we take a look here where we knew this Newton, if we recall from what we said just earlier here, remember a Newton is a kilogram meter per second squared. Here's our kilogram meter per second squared times our meter. That gives us a kilogram meter squared per second squared, which is precisely what we get down here. So in fundamental units, a joule really is this right here. It's a kilogram meter squared per second squared. So I realize I went through that relatively fast, and I probably should have said this at the beginning, but certainly if you need to go back and listen to anything, you can always stop and record and rewind back to see what you need. Hope everything goes well. Talk to you later.